Hello everybody. So in this lecture we are going to discuss about magneto electric effect. Now the primary requirement of this magneto electric effect or ME effect is the coexistence coexistence of magnetic and electric dipoles. Magnetic and electric dipoles, they should coexist. Only then this magneto electric effect will come into the existence. Now this the variation of electrical polarization, the second aspect is when there is a variation of p. P stands for the electric polarization. Uh, this when this occurs, when variation occurs with respect to a change in the magnetic field H, or induced, or the opposite effect, there is an induced magnetization denoted by M by an external field, the electric field applied. So change in P due to H or induced magnetization due to electric field, both of them they ascribe to this ME effect. Now we can write in terms of symbols is as P, sorry, capital P is equal to psi to the power E, susceptibility, electrical susceptibility multiplied by this electric field E, plus electromagnetic susceptibility EM into the magnetic field. This is for the first case when there is a change in polarization due to magnetic field, and for the second case we can write the induced magnetization M is equal to magnetic susceptibility multiplied by the magnetic field applied plus again the magnetoelectric susceptibility into the electric field applied. Now this electrical susceptibility, this one, it is it is a tensor quantity, and so is the magnetic susceptibility M. So is electrical susceptibility, and this is your magnetic susceptibility. Whereas these two quantities, they are called mixed magnetoelectric susceptibility tensors. So whether it is Xi EM Ij, which is in fact equal to the Ji Me, they are mixed magneto electric susceptibility tensors. and they can be defined as, for example, from the equations that we have shown previously, this can be defined as a change in polarization with respect to change in magnetic field, which is again equal to del square phi divided by del EI into del H J, and where this psi or phi, it represents a thermodynamic potential. Similarly, we can also write the magnetic electric susceptibility ME as equal to del M by del E, and that is again equal to del square phi del H I into del EJ, the opposite one. Now, there is a phase transition existing, and so a phase transition occurs when we have a temperature associated with it, which shows these effects, and these and the point at which these phase transition occurs, they are again governed by temperatures. For example, we can have a temperature called critical temperature for electric field, critical temperature for the magnetic field, and they are usually found to be equal. Now, if you relate the susceptibility with temperature, we can write that electromagnetic susceptibility is equal to the magnetoelectric susceptibility, and they are related as T minus the critical temperature to the power half, in fact proportional to. Now, this discovery of this magnetoelectric effect was first found in chromium oxide, Cr2O3. And it has been found that this magnetoelectric effect, this originates due to two phenomena. One is called the magnetostriction, and the second one is the piezoelectric effect. This magnetoelectric effect, this also depends upon the DC bias field, DC magnetic bias field, which can be represented as HO, onto which and AC magnetic signal is imposed. Now, when there is an increase in bias, as this bias increases, H0, the, with respect to the magnetic field, we have something called a Magneto Electric coupling coefficient. So, Magneto, or let's call it as ME coefficient, ME coefficient given as alpha, and it is equal to the change in electric field with respect to the magnetic field at H0. So it is assumed to first increase, reach to a maximum value, and decrease thereafter with a slower rate. Now, this Magneto Electric effect is exhibited by something called a ferroelectromagnetic materials, and in short call them as FEM materials. Now, these FEM materials, like the one previously found, chromium oxide, they can be classified into two types. First, we can classify them as a single phase, having a single phase, or they can exist as composites. Now, these single phase materials, they are basically ordered structure. Ordered structure and require the presence of either ferroelectric or ferroelectric or anti-ferroelectric or ferrimagnetic, anti-ferromagnetic states. And the most important of them is that they should show a two-phase transition. The first one being in the ferroelectric state or ferroelectric state or anti-ferroelectric state, and that will be governed by the temperature TCE, critical temperature, and we have a piezoelectric effect occurring here. And the second one is either it can be a ferromagnetic or ferrimagnetic or antiferromagnetic transition, and it occurs again at a temperature which is TCM, critical temperature for magnetic field to occur, and they are called paramagnetic. PM stands for polarization. Paramagnetic, you can call them as paramagnetic. Or in fact, there is a Niels temperature. So they change phase transformation between these states and the paramagnetic state. Now, in single phase ferromagnetic, the first class of materials, uh, this Magneto Electric effect, this arises due to local interaction between the ordered ferromagnetic states and the electric sublattices. So, so there is a local interaction between these PE states and this PM states, magnetic and electric sublattices. Now, the condition for having both ferroelectric and ferromagnetic properties is also accompanied by having another type of property. It implies that the material is having a ferro sorry ferro elastic property as well. Now, there is also adequate structural building blocks permitting ferroelectric ion movements, and the magnetic interaction pathways usually of super exchange type. So there is a property of super exchange and ionic movements. Now, how can we synthesize a single phase ferroelectric material? The simple way, or the simple explanation, the simple procedure of forming a EM material is to replace any diamagnetic ion by paramagnets. So DM ion, if it is gets replaced by a paramagnet, then the chances of possible electricity exists, and it will occur in an perovskite material. So we have a perovskite, AbO3, and this B, these are the octahedral sites. So at these sites, this following transition should take place. And a good example of ferroelectric anti-ferromagnetic perovskite material is this material, lead Pb, then Fe 1 by 2, Nb 1 by 2, O3. It's called a PFN material. And so this single crystals of PFN, the material represented in short, it turns into a ferroelectric material below if the temperature is less than 9 Kelvin. So you can also place ferroelectromagnetic multiferroics, rare earth materials in the same category. So these materials again show simultaneously ferromagnetic and ferroelectric properties. Now these materials that we have just said, this ferromagnetic and ferroelectric material, their scarcity results from transitional metal d electrons. These d electrons, they are mainly responsible for destabilizing of the off-center Fe distortions. And the example is Bi MnO3 or yttrium MnO3.